Okay, so our third speaker of today is Kianna Wan. She's gonna tell us about fault-tolerant qubit from a constant number of components. Okay, please.
Thank you, and thanks so much everyone for being here. I hope you've all been having a good time at the conference. So today I'll be talking about recent work with Soonwon Choi, Isaac Kim, who we've just heard from, Noah Shutty, and Patrick Hayden. And in our paper, we propose and analyze schemes for fault-tolerantly generating useful cluster states using a small number of physical components, in the hope that this might open up new avenues toward fault-tolerant architectures that are more easily scalable. So our work was mainly inspired by a proposal by Soonwon and some of his collaborators for preparing two-dimensional cluster states. And this was in turn based on the so-called photonic machine gun scheme of Lindner and Rudolph, which prepares 1D cluster states. And both of these proposals sequentially generate photonic cluster states using a single photon emitter. The extension from 1D to 2D is achieved by adding in routers in the delay line, so that the emitted photons can come back and interact with the emitter again. But even though 2D cluster states are universal resources for measurement-based quantum computation, they're not useful resources for fault-tolerant computation. So we wanted to extend the earlier proposals to three-dimensional cluster states. And in particular, we focused on the three-dimensional lattice introduced by Rasendorf, Harrington, and Royal, which they refer to as the BCC lattice. So the cluster state defined by this lattice is a universal resource for fault-tolerant computation. More specifically, given this cluster state, one can fault-tolerantly perform computation by making single qubit measurements in one of three fixed bases. So the perhaps more difficult step is actually preparing this cluster state. And we show how to do this using an experimentally feasible setup, in particular, one that's compatible with existing technologies and also amenable to implementation using a small number of components in these technologies. But at the same time, we need the preparation procedure to be fault tolerant, so that even though the various experimental components are going to be noisy, the resulting errors on the prepared cluster state are still correctable. Okay, so for the first point, we generalized the previous single emitter proposals, making necessary modifications so as to produce the BCC lattice, but the basic setup is the same. You have a quantum emitter, which could be an atom, transmon, or quantum dot, and it sequentially emits and interacts with photons or phonons stored in a delay line. But this kind of single emitter setup seems to be in tension with the second requirement of preserving fault tolerance. You'd expect that if an error occurs on the emitter at some point during the procedure, then that error will spread to all of the qubits the emitter subsequently interacts with. But we'll see why this is okay. Okay, so to get started, let's go back to basics. Cluster states are naturally associated with graphs. Any undirected graph defines the cluster state if we associate each vertex of the graph with a qubit that's initially in the plus state. And each edge of the graph corresponds to a controlled Z gate applied between the two vertices. So this definition immediately suggests a very, at least conceptually, simple procedure for preparing arbitrary cluster states. You initialize each qubit in the plus state, and then apply CZ between each pair of qubits sharing an edge in the graph. So here's an example of such a circuit for this triangle graph. And of course, any BCC lattice we want can in theory be prepared in the same fashion. But the drawback of this approach is that it involves applying gates between all the different pairs of qubits that share edges. And from a practical point of view, all of these gates need to be carefully calibrated and implemented. So to avoid the potential experimental challenges associated with having to calibrate and control an extensive number of these interactions, we consider instead a setting where a single ancillary system, which I'll call a Q, mediates all of the interactions between the cluster state qubits, which I'll refer to as data qubits. So physically, Q can be thought of as an actively controlled qubit, and in the experimental setups we're considering, it represents the emitter, while the data qubits are going to be identical degrees of freedom, such as photons or phonons, and these passively interact with Q. And in particular, these data qubits will be traveling modes which interact with the stationary emitter as they pass by. So as long as there isn't significant variation in the experimental setup over time, each data qubit will interact with Q in the same way. So then it suffices to just calibrate a fixed number of different interactions independent of the number of qubits we want to put in our cluster state. And I should mention another nice feature of using photons or photons especially, is that they don't interact with each other. So we don't have to worry about unwanted couplings between the data qubits. Okay, so under this constraint that every 2 qubit gate can only be between Q and one of the data qubits, how can we prepare cluster states? And the most straightforward thing you might imagine doing is using swap gates to indirectly apply all the requisite CZ gates using Q as an intermediary. So going back to the example of this triangle graph, we can apply the CZ gate between between 1 and 2 by first applying a CZ gate between Q and 1 and then swapping Q with 2. And similarly for qubit 3, which has edges with both 1 and 2, we first do CZ between Q and 1 and another CZ between Q and 2. And then we swap these edges onto 3 by applying a swap gate between Q and 3. Notice also that we didn't have to initialize all the qubits all at once at the beginning. Instead, we initialized 1 qubit at a time and added it to the cluster state. And we can think of this as corresponding to the quantum emitter Q, generating data qubits 1 by 1, sequentially building the cluster state. Okay, so this is all pretty simple, but we didn't end up using this approach because of experimental considerations. So for photonic and phononic platforms, we had a way of implementing swap in single rail encoding schemes of the qubits. But in these single rail schemes, losses aren't detectable because the qubit states are just encoded in by the absence or presence of phonon, for instance. Whereas in a realistic setting, photon loss or phonon loss will probably be an issue. So what we want is a dual rail scheme in which losses can be detected, but we couldn't come up with a method for easily implementing swap in a dual rail encoding. So instead of using swap gates, we used the circuit identity, which was also used in some of the previous papers, to replace a swap followed by a CZ by a C0 gate followed by a Hadamard on Q. And this works for any state of Q as long as we initialize each data qubit in the 0 state rather than in the plus state. And in the paper, we show how these C0 and Hadamard gates can be implemented in both single and dual rail schemes. So by using this trick, you can write down circuits for preparing arbitrary cluster states in which each of the gates are experimentally implementable. But in addition to being able to implement the individual gates, the experimental setup also has to be compatible with the order in which all the different operations need to be applied. So even though this works for arbitrary graphs, you can imagine that periodic structures like a lattice are much easier to realize in practice. So now I'll illustrate how this all works in a single emitter plus delay line setup for the simple example. So I'm going to try to simultaneously draw the circuit, grow the cluster state, and show how the photons are moving around in the setup all at the same time. And we'll consider this 3x3 square lattice with these shifted boundary conditions. And in general, for an L by L lattice, the delay line will have length proportional to L. So here the delay line has length proportional to 3. And as I mentioned, Q can be instantiated by an atom, artificial atom, quantum dot, etc., that emits photons, or the data qubits could be phonons and Q can be a transmon coupled to a phononic waveguide. But for concreteness, I'm just going to say the words atom for Q and photons for the data qubits. So the atom is first going to emit photon 1, and just to clarify, the physical mechanism that implements the C0 gate actually emits a photon with the C0 applied to it. So what I mean is that even though here in the circuit it says we're all starting in the 0 state, it's more like we start in the vacuum state and the atom emits a photon that's entangled with it as would be described by C0. We then apply Hadamard. So remember, together with the C0, this implements swap followed by CZ on Q and 1, which is why you get this edge. Then when we do C0 on 2 and Hadamard again, it has the effect of swapping Q and 2 and applies a CZ between Q and 2. And then same thing for photon 3. But then before photon 4 is emitted, photon 1 will be guided back to the atom, and a CZ gate between Q and 1 will be passively implemented via a scattering process. So then when photon 4 gets emitted, the CNOT and Hadamard will effectively swap this edge with 1 onto 4. And similarly with photons 2 and 5 and 3 and 6, and so on. Basically, the length of the delay line ensures that the photons sort of line up in the right way so that they interact with the atom in the correct order. Now, to implement this to 3 dimensions, we add in a second longer delay line. With a second delay line, each photon will come back to the atom twice before being measured. And this additional interaction allows us to add the cluster state edges along the 3rd dimension. So recall that the length of the first delay line was proportional to L. The second delay line will have length proportional to L squared minus L to ensure that the qubits, again, line up in the right way so as to realize a qubit lattice. And here I've only shown the first part of the circuit, which adds in the first 12 qubits, but the rest of the circuit essentially repeats as you'd expect. The interactions are all nice and periodic. Okay, and to make things even more exciting, if we color in the 2 delay lines, then the corresponding colors on the circuit show you which delay line each photon is in at any given time. Okay, so now we have an experimentally compatible scheme for generating 3D cluster states, but there's still some major issues to sort out. The first is that, well, we didn't just want a way of preparing 3D cluster states. We wanted the procedure to be fault tolerant so that we can then use the prepared cluster state as a resource for subsequent fault tolerant computation. But in the procedure, we had this 1 qubit Q interacting with every other qubit multiple times. So you might naively expect that if an error occurred on Q during the procedure, it'll spread to many, many of the data qubits. And you'd be right, in a sense. So let's consider as an example this smaller 3D lattice, whose circuit I could actually fit on the slide. And suppose that an X error occurs on Q at some point in the middle of the circuit, at this point. Then by using the usual conjugation rules for Clifford gates, we can propagate this error through the rest of the circuit and see that it results in this large error on half the qubits in the final state. But it turns out that under stabilizers of the cluster state, this error is actually equivalent to a single qubit error. So recall for a cluster state associated with some graph G, its stabilizer generators are given by X on some qubit I in the graph, tensored with Z on the neighbors of I. So for this lattice, these are the stabilizers for I equals 8 and I equals 10. And this might not be super obvious from the diagram because I didn't draw some of the edges for the periodic boundary conditions, but these are the correct stabilizers. And if we multiply our big red error here by these stabilizers, then we see that everything cancels out except the Z error on qubit 7. So we see that the large propagated error is actually has the same effect on the prepared cluster state as a very small error. And this is true more generally. So for any single qubit error occurring at any spacetime location in the circuit, including on the special qubit Q, the effect of the circuit level error on the prepared cluster state is going to be supported on some subset of the neighborhood of some data qubit. So it's not always a single qubit error, like in the example we just saw, but it'll always be confined to a local region of the final cluster state. And in particular, if the cluster state graph has constant degree, then this means that the effective errors will all have constant weight. And now I'll sketch the intuition behind why this is true. And let's use the same example as before to illustrate some of the ideas. The first thing to observe is that if a Z error occurs on a data qubit, then it either happens before the CNOT or after the CNOT on that qubit. Note there's only one CNOT on each data qubit. If it occurs before the CNOT, then it has no effect because each data qubit starts in the 0 state, which is invariant under Z. On the other hand, if the Z error occurs after the CNOT, then it'll commute with all of the subsequent gates on that qubit, which are all CZ gates. So the circuit level Z error just ends up as a single qubit error on the final state. And the second key observation is that at each point in the circuit, the instantaneous state of the qubits is a cluster state. And these intermediate cluster states are all going to be closely related to the final target cluster state. So as an example, at this point in the circuit, indicated by the dashed line, the instantaneous state looks something like this. And a few slides ago, we considered the effects of an X error occurring on Q at this point. Now, since qubit 7 is currently the only neighbor of Q, X on Q and Z on 7 is a stabilizer of this cluster state. So this X error is actually equivalent to a Z error on 7. And this Z error just commutes with all the subsequent CZ gates, ending up as a single qubit Z error on the final state, just like we saw before. So the point is, because every intermediate cluster state is basically, every intermediate state is basically a cluster state, that's a subgraph of the target graph. Whenever we have an X error, we can always push it via stabilizers to Z errors on the neighboring qubits, and these Z errors will then commute with the rest of the circuit. And the reason that the final errors are always confined to the neighborhood of some qubit has to do with the way that Q is used to build up the cluster state. So we saw earlier that every time we added in a new qubit, we first made edges between Q and the neighbors that the new qubit is supposed to have, and then we swap those edges onto the new qubit. For example, consider this later point in the circuit. We're about to add in qubit 10, so we have applied CZ gates between Q and the neighbors of 10, which are 4 and 7, and we're about to swap them onto 10. So if an X error occurs on Q at this point, then it'll be equivalent to Z errors on 4 and 7. So this will result in Z errors on some of the nearest neighbors of 10 in the final state. Okay, so this is how you'd prove that any single circuit level error leads to a geometrically local error on the prepared cluster state. And more generally, I'm not going to show this, but if we have M different errors in the circuit, then this will result in M of these geometrically local errors on the final state. And given these results, it's perhaps not surprising that this scheme has a finite threshold for circuit errors, despite the seemingly highly non-local propagation of errors through the circuit. But before we can really talk about error correction, we have to address sort of problem 0, which is that the experimental setup I described naturally realizes the geometry of a qubit lattice, but what we really need to prepare is the BCC lattice. But since the BCC lattice is clearly a sublattice of the qubit lattice, this can be done without changing the setup very much. One way would be to first prepare the qubit lattice and then remove the qubits that are in the qubit lattice, but not in the BCC lattice. And we can do this by measuring them in the Z basis. But another approach is to just have the emitter not emit these unwanted qubits in the first place. So basically you go along adding qubits 1, 2, 3, 4, and 5 as usual, as if you were creating a qubit lattice. But then every time you come to a lattice site that's missing a qubit relative to the qubit lattice, you skip the excitation pulse that would have emitted the corresponding photon, and then you measure Q to disentangle it. Okay, so now let's talk a bit about thresholds for this scheme. We consider the usual depolarizing noise model for what I'll call gate errors, even though these will actually include measurement errors and state initialization errors as well. And we use the basic minimum weight prefix matching decoder. So here's a plot of the logical error rate. This is the physical error rate for storing one logical qubit in an L by L by L lattice for different values of L. This gives a threshold of approximately 0.39%, which is comparable to the threshold for the standard cluster state preparation protocol that Rasendorf et al. Considered, where you just apply a CZ gate for every edge in the lattice. Under the same noise model and using the same decoder, the standard approach has a threshold of around 0.58%. And intuitively, it made sense that we have a slightly lower threshold because in the standard CZ circuit, there's basically 2 gates per qubit, whereas in our circuit, there's around 4 or more gates per qubit. So there's just more opportunities for error under the same noise model. And as shown by Stace, Barrett, and Stace, the BCC lattice is also quite robust against qubit losses that are detectable. So experimentally, if we were to use a dual rail scheme in which losses can be detected, we could do error correction even in the presence of loss errors. So here we consider the same noise model for the gate errors. And in addition, each qubit is lost with probability P loss at some point during the procedure. And here this shaded region is the correctable region of the parameter space, in the sense that if the gate error rate and loss probability are such that they lie in this region, then the logical probability can be made arbitrarily small by increasing the lattice size. But this discussion sort of implicitly assumes that the loss probability is a constant independent of the lattice size. But recall that each qubit is stored in delay lines between its interactions with the emitter. And the length of these delay lines in total depends on the number of qubits. In particular, the total length is proportional to L squared, where L is the linear lattice size. So this means that if the delay line is lossy or otherwise noisy, then there won't be a threshold below which the logical error rate can be arbitrarily suppressed by increasing the system size. Making L larger makes the code better, but also increases the total error accumulated in the delay line. But we'll see that for sufficiently low error rates in the delay line, the logical error probability can be made exponentially small in the delay line error rate. So more explicitly, let eta represent a delay line error rate such that the total probability of error on a qubit due to its being in the delay line is eta L squared for small eta. And on the other hand, the code distance, like the distance of the underlying surface code, is proportional to L. So for a given value of eta and a given gate error rate P, we expect that as we increase the lattice size L, there's going to be a trade-off between the better error tolerance due to the larger code distance and the cumulative error incurred in the delay line, which scales as L squared. So there's going to be an optimal value of L that minimizes the logical error probability. And we can see using a simple scaling argument that this optimal logical probability will decrease exponentially with the square root of eta. And our numerical results agree with this heuristic estimate. So as an example, let's fit the gate error rate to be 10 to the minus 3. And suppose that the delay line errors are dominated by loss. Then we calculated the optimal logical error rates for various values of eta loss and found that it fit the exponential scaling with the square root of eta loss very well. So then a natural question to ask is, for what values of theta is it actually advantageous to use the delay line rather than just not using this error-corrected scheme in the first place? And to answer this, we found the break-even point beyond which the logical error rate becomes lower than the physical error rate of 10 to the minus 3. And from the numerical data, the break-even point for loss is around 7 times 10 to the minus 4. And for comparison, in the optical domain, we estimated eta loss to be around 9 times 10 to the minus 4 for an optical fiber, assuming a generic pulse-to-pulse separation. So this is close to the break-even point, but not quite there yet. And I should mention that even though I've been saying the words photon a lot, another system that's recently been emerging as a promising platform for our team involves a transmon qubit coupled piezoelectrically to a phononic waveguide. And for this kind of system, we saw that dephasing was likely to be a bigger problem than loss. So we did the same kind of analysis for dephasing errors in the delay line, found a similar exponential decay, and also calculated the break-even point. And by our rough estimates, the dephasing rate for a phononic waveguide is also not at the break-even point yet. But phononics is a rapidly developing field, and there seem to be prospects for significant improvements. Okay, so current experimental estimates suggest that we're not at the break-even point yet, but it's perhaps worth noting that once we do get past the break-even point, then because of this rapid decay of the logical error rate with eta, small decreases in eta can lead to very large reductions in the logical error rate. So sure, you need to get eta down to 7 times 10 to the minus 4 to get the break-even logical error rate of 10 to the minus 3. But then if you get eta down a bit further to 10 to the minus 5, you can in principle get a logical error rate of around 10 to the minus 15. And this is without having to improve the gate fidelity. So even if the gate error rate is held fixed at 0.1%, making these small incremental improvements to adjust the quality of the delay line can lead to significant gains in terms of the logical error rate. Okay, so in summary, there's a few different features of our proposal that make it interesting or promising. The first is that it shows it's possible in principle to do fault-tolerant quantum computation with a constant number of physical components. We have one emitter, 2 delay lines, a few routers and detectors. And for sufficiently low delay line error rates, we can scale up the number of physical qubits and suppress the logical error by putting more photons or phonons into the same delay lines without having to add in more control qubits or other components. And this is in contrast to platforms such as superconducting qubits, where each physical qubit often needs to be separately calibrated and controlled. So adding in more qubits requires fabricating and controlling more components. And yet, despite QIP2021, like despite this low component setup in which every interaction is mediated by a single qubit, our protocol is nonetheless fault tolerant with similar thresholds to the standard procedure. And this is thanks to this error correction property that might seem a bit counterintuitive at first. So from a more theoretical perspective, usually to mitigate the spread of errors, we often try to use transversal gates or make intermediate syndrome measurements, do active error correction, etc. Here, we don't do any of that, even though we have a circuit that on the face of it looks pretty bad from a fault tolerance perspective. And yet all circuit level errors lead ultimately to local errors. And this is actually true for using our construction to prepare arbitrary graphs. So it'd be interesting to see whether this kind of idea can be used to design other fault-tolerant protocols. And also an open problem is to perhaps find necessary or sufficient conditions under which a state preparation protocol has this feature. Because this is not a generic property for Clifford circuits, and it's not even a generic property of cluster state preparation circuits. And we provide some counterexamples in the paper. And finally, as a result of these two features, namely the low component overhead and robustness against circuit level errors, focusing on making incremental upgrades to a few key components can lead to significant reductions in the logical error rate. In particular, we saw that even if we assume the emitter error rate is fixed at some high-ish value, small improvements to the delay line error can drastically lower the logical error rate. So focusing on making this one component really good might get us pretty far. And thank you for coming to my talk. And I've left the archive number here in my email.
Okay, thanks for the talk. So actually we got quite some questions on your emitter. So related questions so what do you have any kind of idea what's the physics made of the emitter, or what do you have in mind? What about the loss or error, any other error of the emitter that will be have any? So you made a comment, but can you comment more on that? Also, someone is asking, can you have more emitters, more than one emitters? Would that be helpful? And also someone is asking you, what frequency does your emitter actually need to operate in order to achieve your scheme?
Sorry, can you, can I?
So all about the emitters, can you say more about that?
Sure, so I guess I should say I'm not an experimentalist, so everything I say about the physicality of the emitter should be taken with a grain of salt. So in the paper, what we outline in some detail is more so like the energy level structure of the emitters, or rather the, and we consider some like specific instantiations of the emitter, but what we propose more in detail is more like a class of implementations you can consider doing. For the, so was that the first question? Like, what do you actually use for the emitter? I didn't.
Can you like use more emitters than one?
Okay, yeah, so that was the second question. So yes, part of follow-up work would be to consider what you could do if you just used a sublinear number of emitters, for instance. Like, could you still scale up your system without having to, and get like the smaller scaling of the number of components? And the reason, the sort of special thing about using a single emitter is that all the photons are emitted by and come back and interact with the same emitter. So then things are sort of homogeneous in time. Whereas if you have multiple emitters, one thing we consider doing requires routing photons between different emitters. So like photons emitted by emitter 1 might go and interact with emitter 2 at some point. And this is fine in theory, but I guess experimentally, you might imagine that the different emitters are calibrated somewhat differently. So they might have like slightly different physical properties. But yeah, that's left for future work. And sorry, can you remind me of the third question?
It's okay for now. So I'm asking you another question. So is this a periodic boundary condition essential for your scheme?
Oh, so the periodic boundary conditions are sort of just an artifact of the fact that like after a photon gets emitted by the atom, it's still entangled with the atom. So like once you like loop back around and you create a photon, a qubit in like the next line, the link is still there. Like if you don't disentangle it, your emitter. And that's sort of just for convenience, so that like you're literally doing the same interaction without having to worry about it, like whether you've hit a boundary or not. But to get rid of the boundary, like you could always disentangle the emitter in the middle of your procedure, or you could just create a larger qubit lattice and then measure out the entire boundary. So you only consider the bulk. And when we did our decoding simulations, we actually considered the effect of this, like creating this larger qubit cluster state and then measuring out some of the qubits in the middle as well as the entire boundary and accounting for like measurement errors in doing that as well.
Okay, great, thank you. So I guess we have more questions, but can go to the round table. Thank you.
Okay, sure. Thank you so much.